Hello and welcome to our Knowledge Culture webinar. Today we will be focusing on implementation and optimization of continuous perfusion. My name is Stephen Hume from Whyischer Scientific and I'll be your host today. Before we look at the agenda, let me first introduce you to our webinar console. The navigation bar at the bottom of your screen has several options, and I'm going to run through those with you just now. If you click on any of these buttons, they open and close some of the windows that you have in your screen so that you can personalize the view of your webinar. So button number 1 is your media player, and that allows you to see our presenters today. Button number 2 is the live view of the slides. Button number 3 is for the Q&A. So we will be having a question and answer session at the end of today's webinar. But if at any point during the presentations you think of a question, pop it into the Q&A box and we'll endeavour to answer it at the very end of the webinar. Or if not, we'll send the answer to you via email. The fourth icon that looks like a question mark is in case you need any technical support during the webinar. If anything isn't working for you, click here and we'll try our best to help. And of course, we're always interested to hear if you enjoyed our Knowledge Culture webinars. So at the end of the webinar, you'll have the chance to fill out a survey and tell us what you thought of today's webinar, or you can also access that on the navigation bar as well. So now we're all aware that intensifying bioprocess is one of the key focus areas within the industry at the moment. And this is particularly important in order to achieve cost reductions where they're required by both biopharmaceutical companies and patients alike. Moving to a continuous perfusion process from a batch or fed batch upstream process is often the foundation to intensification. We've got a fantastic agenda for today's webinar discussing continuous perfusion. You're first going to hear about process intensification in cell cultivations from Professor Dr. Dirk Lutkemeyer, who's joining us from the University of Applied Sciences in Bielefeld. We then have Anja Mädler of Octapharma Biopharmaceuticals, GmbH, in conversation with Thermo Fisher Scientific's very own Dirk Tillich, talking about Anja's experience of our bioreactor control software for perfusion. And our last presentation today will be performed by another duo, this time Thermo Fisher Scientific's field application specialist Melanie Ottinger, who will be speaking with Mark Smith, one of our research engineers responsible for the Thermo Scientific high performer DynaDrive single-use bioreactor. Let's find out a little bit more about Thermo Fisher Scientific before we move on to our presentation then. So at a glance, we have 75,000 employees worldwide. Our employees are global thought leaders in all areas of science, and we're able to harness the power of that knowledge for you. Our customers are of the highest importance to us. We have 10,000 customer-facing employees, so we're always there for you. 5,000 of our employees are scientists or engineers themselves, so no matter what you specialize in, we have scientists in-house focusing on the same topics. We are, of course, committed to advancing science and innovating, which is why we invest $1 billion in research and development every year. Our mission is to make the world healthier, cleaner and safer. At our core, we are scientists, and our purpose is to enable our customers to fulfill their scientific purpose. We provide our leading products, services and workflow solutions through 6 brands that I'm sure you'll recognize here. And as represented on this slide, the customer is at the heart of everything that we do. alongside our focus on innovation, productivity, and quality. Okay, time for our first speaker then. With 25 years of experience in mammalian cell culture and downstream processing, our guest was responsible for building up one of the first biosimilar production facilities in the EU. He's been a professor at the University of Applied Sciences, Bielefeld in Germany since 2008, talking about his experience with process intensification in cell cultivations. Please welcome Professor Dr. Dirk Lütkemeyer.
Yeah, thank you for the kind introduction. As you said, my topic is process intensification in mammalian cell cultivation, and I have three bullet points on the agenda. First, I will introduce a little bit the intensification strategies which are in the moment in discussion or sometimes already implemented, and then I will show two case studies from results from our lab. Yeah, intensification strategies in mammalian cell cultivation. Why? Of course, always to cut costs, to reduce process time, and to maximize the facility output to produce biologics. There are four intensification strategies. The first is cell banking. Let's say if you go, normally you have vials, but here, if you want to intensify cell banking, then you use, instead of vials, small bags up to 150 milliliter with a high cell density. And by thawing or such a vial, you can go or jump directly in a bioreactor and skip the subsequent pre-cultures. Second is intensified fat batch, sometimes called concentrated fat batch. Here is more or less a mixture of fat batch and perfusion, but the cell retention device concentrate or retain the product as well. I will show an example. And then third, intensified perfusion N-1 culture. Here, the seed bioreactor is run in perfusion mode. I will show in a minute results. And the last is perfusion culture, but with extremely high cell densities. Okay, first example, perfusion N-1 culture. If you look to the figure or to the picture above, you see the normal standard routine, starting with a cryo vial, and then you have shakers, deflask, whatever, and then you have the N-1 bioreactor in batch mode, and with this culture you inoculate your production bioreactor. For the intensification, then this N-1 bioreactor is run in perfusion mode, and the goal is to have in this seed bioreactor more than 100 million cells per ml. And the advantage to have so many cells in the bioreactor, you reduce the overall process time. It's possible to have a much smaller seed bioreactor. The normal split ratio is 1:5 or 1:10, but now it's possible to have a split ratio from 1:100 or even higher. And in addition, if you like, you can inoculate your production bioreactor with a much higher cell density. We did this in the past, and we started with 10 million cells, and we had then in the following fat batch 30% more product. Okay, to summarize, or what is the advantage? You reduce the operational cost of goods by omitting steps and saving time. But there are disadvantages. Maybe you need costly equipment for the perfusion, continuous centrifuge, or ATF system. The perfusion process is more complex, and you need more cell culture media. Here's a picture from our setup in our lab. In the middle, the bioreactor, and to the right, in the blue box, we have the cell culture media, 50 liter, and this is pumped in to the bioreactor, and the used media is pumped out in another 50 liter bag. The heart of the system, of course, is the bioreactor itself. Here we used a single-use perfusion bag. And in our, here for this results, we used a 2 liter bag with 1 liter cell culture. And in the middle, you see this white sheet. This is a cell retention device. It's a 1.2 micrometer membrane, which retains the cells. We used for our cultivation CHO cells, producing monoclonal antibody. Culture conditions were more or less standard, and we had for our results 2 different Whyischer Scientific high-performance media. One is called HIP CHO, and the other one is a GIPCO prototype. And these media were supplemented with glutamine, anti-clumping agent, very important, and a lot of glucose. Here are the results. If we start with the left picture, here the growth curve in black dotted line. Until day 9, we saw a nice exponential growth. After that, a more linear growth. And after 15 days, we reached more or less 100 million cells, maintaining a low perfusion rate, and we had a high viability. If we look to the right, then with the GIPCO prototype medium, the exponential phase was longer until day 11, and we reached here a maximum cell density of 160 million living cells per ml. This was the highest cell density we had so far in our lab. And even, or let's say, if we look to the viability, is very, very high. Looking for the metabolites, the arrow in both pictures indicate 100 million cells, and up to 100 million cells we saw no limitation of the, glucose or glutamine, and very nice, we saw the metabolic shift, and day 7 then lactate is consumed from the cells. And these results show that the single-use perfusion bioreactor we used worked really well, and both media were able to get 100 million cells, maintaining a low perfusion rate. Now I want to switch to the second case study here. I want to explain intensified fat batch. In our case, we used the ultrafiltration cartridge with 50 kilodalton cutoff to retain the antibody in the bioreactor. And cell line and media was the same as I showed before. Here in this case, we used HIP CHO with the same supplement I mentioned already. Here are the results. First, let's have a look to the left. Nice growth curve until day 10. We had exponential growth up to 120 million cells per milliliter. The perfusion rate was low, 2. In this case, 1.2 reactor volumes per day. If we look to the middle, we saw a limitation of glucose on day 9. This is the reason why the cells stopped growing and arrested in the stationary phase. And to the right, here is the product, the accumulation of the product. We reached in this 2 liter bioreactor 2 grams per liter. And comparing this with a simple fat batch we did with the same media, we had an 8 times higher product concentration. To conclude my talk, intensification of cell culture processes are possible, in our case without high investments. So we had no ATF or continuous centrifuge or other devices. It was possible to get extremely high cell density, above 100 million cells, and we saw no aggregates at all. That was very important. The overall high-performance media like HIP-CHO or GIPCO prototype generates extremely high cell densities, obtaining a low perfusion rate, which is really important to have a low perfusion rate. And if you look a little bit closer to the media, then the GIPCO prototype is a richer medium compared to HIP-CHO. I have to thank my students in the lab, and I have to thank you for your attention.
Thank you very much, Dr. Lutkemeyer. Very interesting indeed. Moving on to our second presentation today, our next industry speaker is an engineer in biotechnology who's been working on perfusion processes to produce recombinant proteins in HEK cells at Octapharma for 8 years now. I'd like you to give a very warm welcome to Anja Mädler. Hi, Anja, how are you doing?
Hey, thanks, I'm good. How are you?
I'm good, thanks, I'm good. And joining Anja today is a gentleman who's been working within the process automation function of Thermo Fisher Scientific since 2008. In Europe, he's been responsible for setting up and growing the bioreactor control systems business. My colleague, Dirk Tiller. Hi, Dirk.
Hi, Stephen. So I guess I take over here. So thank you very much, Stephen, for that introduction. I'm very happy to have Anja with me here today. She agreed for doing the interview. We prepared some slides for the audience. And so there are some photos Anja took at Octapharma. And let's see how it goes. Hi, Anja.
Hi, Dirk.
So we met in 2015 at Akima, and I'm just interested. Why were you interested in our bioreactor control system? What were you looking for, and what were the expectations?
So we planned to get a new 4-fold parallel bioreactor system by that time. So that's why we went to Akima to find some information about different small-scale bioreactor systems and to find out which provider would give us the best possibility to combine our different needs, which was that we wanted to be able to work with automated perfusion in small volumes, also down to 1 liter. So we needed the option to integrate the biomass probe, but as well wanted to meet the requirements to have a good downscale model for our pilot plant. And as the process regulation is a bit more complex with perfusion, we were not only looking for reliable, but also an intuitive regulation and data recording. So when we were there at Akima, we ended up talking about I think 2 hours with Dirk about our needs, and he explained the software to us quite well. So in the end, we left pretty amazed by the possibilities the software offers.
Yeah, well, I well remember the time we spent. We had intense discussions about the control and possibilities we could offer to Octapharma. To better understand your setup, could you explain a little bit what your setup is, and maybe also give us some insight about the perfusion rate?
So our aim was to work with 1 liter working volume, possibly also with 2 liter. So for regulation purposes, the bioreactor and the ATF are on a balance, which needs to be integrated in the software. So that way the volume can be kept constant within a certain range during the whole process. We have 4 additional balances for feed, bleed, harvest, and base, but they don't necessarily need to be integrated. But if you want to track it online as well, then you can integrate them as well. For the perfusion control, as well as regulation of the cell density, we have the integrated biomass probe. And as you can see on the picture here, the control tower offers 4 pumps that we use for feed, bleed, harvest, and base. But we have 2 additional external pumps, from which we use 1 for the antifoam in our standard processes. And also depending on the process, we use 4 or 5 mass flow controllers for air, oxygen, and CO2. And all mass flow controller outputs can be assigned to the 3 different gas output connectors, just as you need, like for aerating headspace or with dispatcher. The challenge of automated perfusion in small vessels is definitely to integrate all the probes and ports in the head plate that you need. So it was possible that with some customizations that we design a 1 liter vessel that have all the 5 ports that you need for the 12 millimeter probes and the condenser and the ATF dip tube, as well as all the addition pipes, dip tubes, and other ports like for sampling, feeds, sparger, and so on.
Yeah, thank you for explaining your setup, Anja. You mentioned an online biomass sensor. Does your control strategy include bleeding based on an online measurement of biomass?
Yes, so the capacitance measurement is included in the software. So we can use this parameter to regulate the feed rate, which allows us to have a cell-specific perfusion rate also in cases of unpredictable growth rates. And additionally, we use it to regulate the bleed pump to keep a constant cell density during the production phase. And then the harvest pump is kind of indirectly regulated by the biomass via the feed and the bleed pump.
Yeah, indeed, integrating additional sensor signals, etc., is quite easy with our system and our software. However, there are several brands in the market. Can you tell us some of the main reasons you decided to choose Whyischer Scientific?
Yeah, so as I mentioned before, it was quite tricky to implement all the probes and ports in the small bioreactors. But with Thermo, we were able to design a 1 liter vessel that suits our needs. But I think probably the biggest influencing factor was the software. That is kind of like a programming toolbox, let's say, where you don't need any script to set up the perfusion regulation. And still the visualization is very good too. So the system provides quite high flexibility as well. For example, it's possible to connect bioreactors from other vendors just with another motor adapter. And the fact that it's a modular system even increases flexibility further. For us, it was also possible to, or in general, it's possible to choose the mass flow controllers with ranges that suit the needs of your processes and the bioreactor size, and same for the pumps. And last but not least, as space always is an issue, especially with big setups like you have for perfusion processes, the footprint of the control unit played a role for us too. And as you maybe can see on the picture, we have lots of different colors for our control units, which wasn't really influencing our decision, but we're quite happy with this because it makes it way easier if you look at graphs, if you stick to the colors of the units. So to keep an overview, it's quite handy.
Mm-hmm. Yeah, so yeah, I very often heard about the footprint advantages, and actually we don't have any connectors on either side of the control towers, so you can even pack them closer to each other. And as there is no display on it, you can even put it beneath the bench. So that's pretty handy actually. So let's talk about system expansion. So the software and the system can expand with additional control towers and vessels. Did that play a role in your decision to go with us?
Yeah, also, because initially we planned, and then we also bought 4 units with 1 liter vessels. But we wanted to have the option of expansion if we are satisfied with the system. So yeah, the easy expansion with just some further control towers to connect to the existing to logic influenced the decision as well. And then actually after 1 year, we upgraded to another 4 units to have 8 in total, again with 1 liter vessels, but we also made use of the ability to connect larger vessels. So we upgraded to another 8 3 liter vessels as well.
Okay, yeah. So, but now you have multiple vessels, huh? And you might want to transfer your process control strategy from one vessel to another. How do you transfer the process regulation between those vessels, or even 2 vessels in a different size?
Yeah, so we use the option of setting up the programming once at one unit, and then we transfer the programming with the save files to the other units. So all parameters are saved in those, so only small adjustments have to be made if you have like different settings in the different bioreactors, for example, I don't know, maybe different temperatures or different perfusion rates. You just need to do small adjustments. And yeah, also the transfer to other scales or vessel types is quite easy. So if it's just different scales, you just need to adjust the working volume in the calculations, for example. If you want to transfer to bigger vessels, for example, like the 50 liter soap, you have to consider that the ATF is not on the balance, which in this case are the load cells. So you need to adjust the regulation for this a little bit more, but it's not that much too.
Okay, yeah, absolutely correct. So TrueBio can actually save somewhat about 4,000 parameters describing the vessel and the process control parameters, etc. So, and that's saved then in that save file you just mentioned in, well, it's a part 11 compliant file actually, and you can use that setting then again and again, even after a year or multiple years later. So let's talk a little bit about remote access. Logging into TrueBio allows you to get into TrueBio actually through a web browser, so you can act remotely on the platform. How has that been for you in your experience, in your environment?
Yes, so we necessarily use remote control on a daily basis, as our bioreactors are split to 2 labs, and so 4 of them, we only use remote access to control them. And also we use the remote access from the office all the time to have an eye on the processes during the day, or if we do small changes, we don't have to wait for the reaction in the lab or get changed all the time, go in the lab and out again. So this is quite handy in the daily routine. In mandatory cases, we also use the remote access from home, especially, for example, on weekends. It's sometimes quite helpful to be able to check on the process later on again, because you're in the lab just for a few hours.
Yeah, so great to hear about your experience using the remote access option we have put into the system. You mentioned earlier the flexibility of our system. So especially when looking at the software to adopt your desired control strategy, TrueBio offers quite a value. How complicated is it then to operate actually the software?
Yes, so initially it's lots of functions to learn and to get to know the setup of the software. But there is 2 days TrueBio software training that is offered by Thermo Fisher. And this actually is really helpful and needed as well. But after that, if you have some hands-on practice, with what you have to do anyways, because you have to set up your process, then it becomes really intuitive and easy to use also for challenging purposes.
Okay, so thank you. You just confirmed what I heard from many TrueBio users in the past. Actually, probably about 95% of our users, probably even more than that, are using the standard configuration of TrueBio. So some people, some clients want to have some customizations for whatever reason. My question is, as we are talking here about perfusion processes, can you do that just by using the standard set of TrueBio functionalities? So no customizations, just standard TrueBio?
Yes, so we actually belong to the 5% that we have an additional logical function block, but only because at first we weren't totally sure if one would be sufficient with the programming of the perfusion. But it turned out that for our normal processes, the regular set is totally sufficient. So yeah, we normally don't use the second logical function block.
Okay, so you can do your perfusion at least without any customizations. That's great.
Yes.
Well, we are at the end of our conversation here, Anja. So you have been using the system for about 4 years now. Can you summarize what differentiates this system from other systems that you know?
Yeah, so to point out one more time, definitely it's the software that enables the complex programming without scripting language. And at the same time, it's still being displayed very clearly. Also, the data visualization with history and data is quite clear and flexible as well. So you can compare 8 different parameters in one graph where they can be from one or different vessels, just as you wish. And you can also have a look not only on current data, but also on historical data. Sometimes it's quite handy that the data is logged non-stop and you just extract the time range that you need to look at. And the flexibility that the modules bring along. So if you want to process with a larger bioreactor, for example, and your mass flow controllers are not sufficient anymore, you can just exchange the mass flow controller box and it will be recognized automatically by the software. And then if you want to switch back to your smaller vessel, you can just connect your mass flow controller box that you have for the smaller vessels. And yeah, for us, like in our case, the big difference was as well the possibility to have a full automatic perfusion in 1 liter working volume.
Okay, well, thank you very much for sharing your knowledge with us, Anja. It's been really a pleasure to hear about the experience you got over those 4 years with the TrueBio system. So thank you, but also a big thanks to the audience. And please remember, if you have questions, there's that Q&A button on the bottom of the presentation platform. So just use it, please. And with that, I'm handing back to Stephen.
Thank you both. Thanks for that great presentation. Great to hear you about your experiences there, Anja. And as Dick said, please remember to put your Q&A questions into the Q&A box. We will be having that session at the end of the webinar to cover off any of the audience questions. So let's turn now to look at one of Thermo Fisher's latest technologies that's promising to enable a next generation of upstream processes, including continuous processes. It's the newly released high-performer DynaDrive single-use bioreactor. One of our field application scientists, Melanie Ottinger, is here to discuss the DynaDrive sub with one of the bioprocess research engineers behind its development. We're very lucky to have with us today Mark Smith. Hi, Melanie and Mark.
Hi.
Hi.
Thanks, Stephen, for the kind introduction. And also, Mark, thanks for waking up so early and being here to discuss the high-performer DynaDrive sub as one of the lead application engineers from the development team. We are excited to hear more about the DynaDrive technology. So will you please give us some history and details about the DynaDrive sub?
Yeah, Melanie, I'm happy to be here too, although it is a little early for me. But yeah, Thermo Fisher is really excited to be releasing this, what we consider a truly next generation of single-use bioreactors. And with all these processes changing in bioprocess industry, particularly things like continuous processing, Thermo Fisher wanted to take our almost 2 decades of experience in single-use technology and really provide an unparalleled mixing and mass transfer system that also offered the end users unprecedented levels of ease of use through ergonomic design enhancements, as well as tying with the automation that Dirk and Anya just spoke about. And so we're excited to announce we've launched the 50-liter version of this officially just a few weeks ago, and the 500-liter, 3,000-liter, and 5,000-liter models are coming in the next coming months.
Yeah, that sounds promising, very good. But I think it's also interesting to know for us how does the DynaDrive sub deliver performance and functionality for continuous processing in particular?
Yeah, so kind of 2 parts to your question I see. One is performance, and that's what happens inside the reactor, and then one is functionality. How do you interact with it? How does the operator interact with it? What are logistical challenges? So I'll answer it kind of in those 2 frameworks. So first, in terms of performance, DynaDrive can reach up to 80 watts per meter cubed power per volume across scales and provide mass transfer coefficients, or KLAs, in excess of 60 inverse hours. To provide context to that number, a typical mammalian cell culture of maybe 15 million cells per mil may only require KLAs 4 to 6 inverse hours. So the DynaDrive can provide more than 10-fold the requirements of what cultures in the past have demanded. And this is really moving towards enabling then high-intensity processes like were spoke about by Professor Luchtemeier this morning, or just today, I should say. I'm so stuck in my time zone. But through this level of performance, we've achieved this level of performance through multiple technologies, but critically, it's named the DynaDrive, and the DynaDrive is really the essential namesake part of it, right? If you look on the slide there on the right image, you kind of get an idea of what the DynaDrive is. The DynaDrive is the flexible drivetrain that carries and drives the impellers that have been optimized for mixing and performance. So not only is it optimized for performance, but it's also flexible. So it can be folded down for easier packaging, easier manipulation, and then easier disposal. And so kind of all of these aspects of the design, particularly the DynaDrive, really bring that excellent mixing and mass transfer. And finally, we can have really high turndown ratios. If you look at that picture on the right, you can see that the liquid volume levels we can mix down to are very low. For example, in this case, it's 20 to 1 turn down in a 500 liter, or 25 liters mixing in a 500 liter. So that's kind of the performance side of it. In terms of just functionality towards continuous processing, of course, naturally, the performance enables the continuous processing, high intensity cultures. But in addition, we've designed the DynaDrive sub from the bottom up or from the start with continuous processing in mind. For example, we can see in the slide, if you look on the left image or even on the middle image, that the front doors of the 50-liter and 500-liter have been designed with large access ports all the way up the front face of the reactor. And this is purpose-built so that it's not just a viewport, but really it's a place where we can put in very large ports for cell retention devices like TFF or ATF systems. So this is just one example of how we've built kind of a standardization of flexibility into this new next generation of bioreactors, or the DynaDrive.
Yeah, thanks. So in order to make our conversation a little bit more hands or practical, can you provide us with some examples of how the DynaDrive has been used in intensified or continuous processing?
Yeah, absolutely. And naturally, within the course of launching a new reactor, Thermo Fisher continuously is testing that in-house. And we're also testing that with a variety of partners and have tested scales from 50 to 5,000 liter scales with partners. So from this testing, specifically in regards to kind of a continuous processing, we've seen some really exciting results. So one example is we've seen one partnership where we had steady state perfusion where the viable cell density was in excess of 300 million cells per milliliter in the 50-liter. So in another case, we were looking at an N-1 perfusion prior to an intensified fed batch process. And the DynaDrive in this N-1 perfusion, yeah, non-steady state, right? But it was estimated that the DynaDrive could support up to 400 million cells per mil based on the oxygen transfer rate versus the oxygen uptake rate of the cells in that culture. So again, for perspective, if you take cells and spin them in a conical tube around 100 G, you're going to typically have somewhere on the order of maybe 380 to 500 million cells per milliliters. So in other words, we project that the oxygen transfer capabilities of the DynaDrive are sufficient to sustain cultures up to the literal physical limit of the volume of the cells. So this is just an example or a couple examples of that highlight the performance of DynaDrive and how it can support even the most demanding cultures.
Yeah, sounds good. I'm always curious. So can you give us some other examples of how the features of the DynaDrive can have leveraged?
Sure. Yeah. So there's, of course, hopefully with most new products that are really trying to provide the next level of performance and usability to customers, there's lots of features. But one of the ones I find the most exciting is really the turn down ratio. So for example, with a 50-liter DynaDrive that has a 10-to-1 turn down ratio, so one could seed the reactor at 5 liters. And in one case, leveraging low turn down capabilities, we've actually seen seed trains where the 50-liter DynaDrive can be directly inoculated from high density cell banks, effectively completely cutting out the need for any kind of open operations in incubators or small volume rockers or wave reactors. In another example of using the low turn down, we actually used low turn down in a 5,000 liter, where in a 5,000 liter, we did an N-1, N-2, and the final fed batch stage all in a single BPC or bioreactor container, or bioprocess container, I should say. And that ability really enables you to take away all the additional reactors in the seed train that would be necessary to obtain up to 5,000 liters. And that takes away consumables and cost, labor and connections. So a lot of things can be taken away by leveraging that turn down. So that's why, really, to me, the turn down on the DynaDrive plays a really exciting role in how we can make bioprocesses more streamlined and sustainable as we move into the future.
Yeah, I definitely like the aspect of more sustainability. Mark, with your experience, if you could leave this group with a single takeaway thought, what would it be?
Yeah. So, with a single takeaway thought, would really be that the single-use bioreactors of the past were designed to meet the bioprocess demands of the past. And so with new culture modalities like continuous processing and new types of cells being used, new culture modalities, really there's a choice to limp along or make do with the moderate improvements of the reactors of the past, or you could make the choice to move forward with more confidence with something that's really designed, purpose-built to the needs of the bioprocesses of today, like the DynaDrive sub.
Yeah, Mark, many thanks for your time and sharing some exciting details with us about the DynaDrive sub. Thank you.
Thank you. It's certainly been my pleasure.
Well, thank you very much, Melanie and Mark. We really appreciate your time and insight to discuss such a great product. And I love the fact that you both had managed to coordinate your wardrobes and be brand colours for Thermo Fisher Scientific as well, with the red and black. So good job. Really good job. Okay, quick poll for you today then before we move on to our question and answer session. So this is a knowledge culture webinar, and we also run knowledge culture seminars, which are more one-to-one based. So in a seminar, your company can select a number of topics, and we'll organise for a team of Thermo Fisher Scientific experts to give you some of the latest insight on your chosen topics. So the question is, would you like us to get in touch to organise a free virtual seminar with you? Your answers could be yes about single-use technologies, yes about downstream purification, yes about cell culture, yes about another topic. Maybe there's another topic that you're dying to hear about and we could help with, so we could discuss that. Or maybe you'd like us to get in touch next time if you're not looking for a virtual seminar. So would you like to get us? Would you like us to get in touch to organise a free virtual seminar with you? And you can select one of the various answers there. One more reminder as well that there will be a survey at the very end of the webinar. We're keen to always find out what you think about our knowledge culture webinars. So at the very end of the webinar, when the survey pops up on your screen, we'd really appreciate it if you can take a couple of minutes to fill out that survey. But let's move on then. I'm going to close off that survey. We've reached our question and answers session. So there have been plenty of questions coming in during the webinar, and we've got about 10 minutes or so to run through the questions that have come in. The first question is for Dr. Lukemeier. I'm going to throw this one out to yourself. It's from Frank, and Frank would like to know, are standard bioreactors like wave type or benchtop able to supply enough oxygen to the culture without creating a lot of foam? Dr. Lukemeier.
Good question. Good question. Interestingly, in the wave-type bioreactor, we had no problem at all to supply enough oxygen without creating foam. So maximum 50% of the incoming or in gas was pure oxygen, but it was not necessary to use antifoam. In contrast, this 2-liter bioreactor we use for the intensified fed batch, here we had foam and it was necessary to add antifoam.
Fantastic. Thanks very much for that answer. Our next question is from Chiara, and this is probably one for yourself, Anja, and Dirk Tillich. Can you please tell us the duration of the process and specify if it's an N1 perfusion or concentrated fed batch perfusion or intensified fed batch perfusion or continuous perfusion?
Well, so the duration of our continuous perfusion processes That's what we run in the thermal systems. Totally depends on the product, but roughly I can say that they last from like 2 weeks up to 4 weeks.
Great, thank you. And sticking with yourself then, Anya, I've got a question here from Francesca. She's asking, how many viable cells do you get approximately?
I think my connection is quite bad right now, but can you hear me?
I can still hear you, yep. I see your video's frozen, but we can still hear you, hopefully. We'll come back to that question. We'll come back to that question, Anya, if you want to refresh your browser. So we'll go to this next question from Paul. This one's for you, Mark. Why did you choose the cubic format and the innovative mixing?
Sure. So, of course, let me answer that. From an innovative mixing perspective, we wanted to provide a variety of things. One, of course, just maximize the mixing at a given power input so that we could ensure good mixing across power inputs. And as well as distribute the impellers so that the power input is distributed. If you have a single impeller and you want to get to very high power inputs, the gradient of power inputs in the vessels is very large. So we don't want that. That's why we have multiple impellers, optimally spaced. And then second part of your question, really, first part, is why did we go to a cubic orientation? There's a variety of reasons, but one of the primary reasons is that when you go to a cubic orientation or format, you actually, effectively, the corners in the reactor can act as baffles. And as the fluid rotates around the internally, as it hits a corner, it gets diverted up and down. And that then enhances your mixing, which then enhances your mass transfer. So that cubic format really does play a critical role in the overall performance of the DynaDrive.
Great, thanks, Mark. Dr. Lutkemeyer, coming back to yourself, we have a question here from Per, and he's asking, have you seen clogging of the cell retention devices, for example, perfusion membrane or hollow fiber cartridge?
Yeah, if we look to the perfusion bag or the wave-type bioreactor, here we saw no clogging at all, but we had only cultivation times up to 20 days. So, and in the end of the cultivation, we saw a changing of the membrane from microfiltration to the more ultrafiltration membrane. So, yeah, but no clogging. In the 2-liter system where we use this hollow fiber cartridge, yeah, if we used higher perfusion rates, let's say 3 or 4 reactor volumes per day, then we saw clogging, but not maintaining a low perfusion rate.
Thank you very much, Dr. Lutkemeyer. Mark, back to yourself for this one, I think. Why did you decide on the unique drivetrain for the DynaDrive instead of commonly used impellers? That's from Alexandra.
Sure. So, as I mentioned a little bit, but we've not only gone to this drivetrain that's unique, but also to some uniquely optimized impellers. And of course, the drivetrain itself provides two things for us. One is well, actually more than two things, but one thing is it's very, very flexible. So it allows us to package even very large reactor systems relatively small, which means then just usability inside of a facility goes up. Also, post-reactor disposal, I think is something that isn't always taken into account, but how do you decon or autoclave a biohazard bag that's 3 meters by 3 meters, right? So we wanted to make sure that we could also compress it after the culture. And then another reason we went to this drivetrain is that if you go to a traditional shaft and you wanted to get the same power input that we wanted to get, your shaft's diameter is going to grow substantially. If you're at 5,000 liters in a stainless steel bioreactor, you're looking at a shaft that is maybe 10 centimeters in diameter, very large. And how do you make something that's sustainable but disposable at 10 centimeters in diameter? So we needed to look to a novel approach to deliver the power and the torque we needed for the cell culture while being more sustainable in terms of how much material was going to be disposed of, and more flexible in terms of how we could package it and how we could dispose of it. Does that answer your question? I guess, Alexandra, we can't answer that. Alexandra can't answer that.
We'll find out later if it answers the question. We will get in touch with everybody to make sure they're happy with the answers. I think we've got Anya back. Can you hear us, Anya? Maybe not. Let's keep going with a question for Dr. Luckmeyer again. This is one from Carl. Did you use powder or liquid media? If powder was dissolving the media an issue?
Okay, we used both. Of course, if you use liquid media, it's always very convenient, but we had powder as well. And sometimes for dissolving high-performance cell culture media, it's really a challenge. You have to add different things, and you have to adjust the pH in different direction to dissolve all the amino acids and so on. But that was not the case here with the HIP-CHO or GIPCO prototype. It was very easy dissolving, and it was only necessary to check the pH. And so very, very handy.
Thanks, Dr. Luckmeyer. Okay, Anya, we're going to come back to you for that question that we missed. So the question was from Francesca. It was, how many viable cells do you get approximately?
Yes, so also this depends a lot on the process and the product. And processing and fusion, it's not only about how dense I can get my cells in the bioreactor, but also what is the capacity of the ATF filter before it starts clogging, so product could be retained. So in the end, it's always the aim to find the balance between cell density, perfusion rate, and actually the duration of the process. But the range in which we have experience, I would say, is roughly between 10 and 30 million cells per milliliter.
Thanks, Anya. I'm glad you managed to get back online with us there. We've still lost your video, so apologies to the audience for that slight technical hitch there. Dirk Tillich, you mentioned the TrueBio software training. We've got a question here. Is it only held at Thermo Fisher facilities, and where?
Okay, well, yeah, in the times of COVID, of course, it's always a little more tricky. So with all the travel restrictions, etc. So we do right now the trainings just remotely. Normally it's a 2 days training that we would provide at the customer's site, or as a kind of a public training in at the Thermo Fisher facility or a hotel where multiple companies can send in 1 or 2 of their employees to get a fresh up, or if they get new to a department, to get trained. With the remote training, we are shifting to a 4 days, half-a-day training, so that people can survive those online sessions.
Great, thank you, Dirk. Dr. Luckmeyer, we have a question from Marco for yourself here. He's asking, have you tried high cell density processes with hex cells? And if yes, which cell densities have you reached?
No, unfortunately not. This intensification we had only done with CHO cell lines up to now. Sorry.
No problem. Quick answer. Sorry, Marco. Okay, Mark, we've got another question for yourself here. What is the Dynadrive sub-seat train turndown ratio?
Yeah, so it's slightly different across scales, but on the 50-liter scale, it's 10-1. So that's 5-liter operation in 50 liters. And that at that 10-1, or at that 5 liters, you also have at least 4 of your probes covered. So that's 50% of your probes can be covered there. 100% of your probes get covered at 10 liters or 5-1 in the 50 liter. In the 500 and 5,000 liter, it's a little bit different. We actually get up to 20-1. So it'd be 25 liters in the 500 and 250 liters in the 5,000. And in those cases, actually 100% of your probes are covered at the very low turndown. So there provides a lot of flexibility in terms of what one could do in how one formulates a seed train.
Great, thanks, Mark. And we're just over time, but I'll squeeze one more question in for yourself, Mark. Scott's asking, have you tested cell aggregate size distribution control by modulating the agitator speed?
So we haven't tried this specifically to try to control the aggregate as yet, which is not normally, or at least traditionally for most operations that I'm aware of, you would want to minimize your aggregates. And so we have looked at, at nominal performance, at full volume, what is your cell aggregate level? And we see very low aggregation. However, it could be something that could be very interesting to be explored, because we do maintain mixing even at very low power and shear levels. And so that you could potentially play with that and tune that a little bit. But no, we have not explored that fully.
Thanks, Mark. So I'm afraid that is all we have time for in today's Knowledge Culture webinar. I do hope you've taken something from the webinar on continuous perfusion. If you did ask a question that we didn't manage to answer, then don't worry, we will endeavour to answer it via email. And please do fill out the survey that will pop up on your screen as the webinar closes. We're always really keen to hear your feedback on how we've done. So thank you very much for your time today. Stay safe and have a great day. Thank you very much.